Thank you guys. I'm really sorry I couldn't be there in person. I had some unskippable family things, but I it's all the more regrettable because I've been to a couple hybrid conferences and I know how terrible the remote talks are. So I apologize. I will do my best to keep you interested and not just a talking head in the corner of the room. Um, I haven't seen you guys. I kind of consider this my community where I'm most home, feel most at home since the conference in Spain, I guess, which was before this little pandemic happened. And so when I was putting together this talk, I wanted to be able to say, hey guys, I haven't seen you in a couple of years. Here's what we've been up to during the pandemic. And the title, I think, sort of summarizes it about as well as I can. We've been doing some quantum chemistry, of course, but we've been moving increasingly into looking at how to do quantum logic for molecular ions. And so the outline really reflects that. I want to start off by telling you about a chemistry experiment we did where I'm really delighted with this because I can say it's really chemistry. For many years, when the chemist would hear about our work, they would say, "Oh, that's cute, that's interesting," but that's not really chemistry. I'm not even sure ytterbium is a real atom. You know, so this is a reaction of carbon ions reacting with water, and even the most skeptical chemists have to agree that those are real things. And it ended up being interesting because it illuminated, for me at least, what do we mean by a branching ratio in a reaction? And it turns out that I don't think that quantity is actually very well defined, and I'll explain why. Then I want to segue to sort of the quantum logic part of the talk. I'll tell you about two ideas. I've been working sort of our pandemic project. A lot of this is done with Wes Campbell, my colleague at UCLA, has been just thinking about ways of doing quantum logic with molecules. I'll tell you about my sort of favorite two that we've come up with. The first we call dipole-phonon quantum logic. It effectively lets you do quantum logic spectroscopy of molecular ions, but where you can replace one of the lasers with a battery and a potentiometer, which is a pretty big win. And then I'll tell you about something we're calling electric field gradient gates, or EGGs. And this is I'm excited about this because not only is it a laserless way of controlling molecular ions, it also works for ions in thermal motion. So you don't need ground state cooling. All right. Okay, so the platform for most of these experiments, I think you guys all know and probably have similar ones in your labs, is the motion trap. You know the drill. We have the ability to make a magneto-optical trap, some ultra-cold atoms, and also do some trapped ions. And what I'm going to talk about today, we actually don't use the neutral atoms. We can load, ions into this trap. We can load molecular ions into this trap. And when we're done, we see something like this where we have a couple of dark ions, which are our molecules. We can also use this to look at chemistry. Here's a picture where, ion number 34 or whatever, atomic ion number 34 became molecular ion number 1, right? And using this integrated mass spectrometry technique developed by a couple of my former group members, we can hit a button and get the mass spec of everything in the trap with way better than isotopic resolution. So this has become a sort of a general purpose chemistry tool for us and others in the field. And it's been a lot of fun using this to learn something. And so it's in a platform like this that with the team showed here, Wes, my colleague at UCLA, Hua Gao, many of you may know at New Mexico, and Arthur Suits, that we wanted to study some quote unquote real chemistry finally. So what we did was built a system that could trap carbon ions, and we had to learn how to laser cool beryllium ions so that we could sympathetically cool those carbon ions down because they're quite light. So you get, the starting point is something like this, where we have some beryllium ions, and then the dark spaces are carbon ions. Oh, I should also point out, this is a little bit self-serving, but Tiangang was an amazing postdoc in our group. He's now a professor at SUSTech in China, and he's starting off a new experiment to basically take these techniques and apply them to chemistry. He's a chemist. So, if you guys are in China, look him up, or if you're organizing a conference, it'd be great to pull him in and help him get started. All right. So using this system, this ion trap that's sort of here, we wanted to be able to put in sort of anything to react with these carbon ions. And so we built a sort of general purpose reaction machine where we had a cryogenic buffer gas beam. So this cools down to anywhere, it can get down to 3 or 4 Kelvin, usually run a little bit hotter. We can make a buffer gas beam and we shoot that over to the trapped ions here where we can let them react and then analyze the reaction. And all this business here is really just about differential pumping because, you have a pretty big gas load and you want to keep ultra high vacuum over on the right. And so what happens, you have your trapped ions, you shoot cold stuff at it. And using this, we studied a number of reactions right away. And the one I'm going to tell you about is this carbon ions with water. And this is actually this is a fun reaction because it has a couple of features that are interesting. One is the reaction produces the formal ion and a hydrogen, but there are 2 isomers of the formal ion. You can have HCO plus or COH plus, or if you read it the other way, HOC plus. Effectively, the point is the hydrogen can be bonded to the carbon or the oxygen. And this reaction is important in interstellar chemistry. Its low temperature product ratio of making these 2 isomers had never been measured. There are networks in the interstellar medium that produce these things. And interestingly, the astrophysicists use the ratio of these 2 things to learn something about these molecular clouds. So one of the things they use it for is this ratio, they say, is a good marker for whether some cloud is in some photodissociative region. What that means is there's some star nearby producing a lot of UV photons, for example, that are breaking molecules apart. And so they want to learn about that part of the star, sort of how dense the cloud is by seeing how penetrating that radiation is. And they use this ratio to learn about the structure of that cloud. However, that ratio it's important to know the reaction that produces these things, their branching ratio, and that had actually never been measured at low temperature. It had been measured at 300 Kelvin, and that was the value that was used for all these models for decades. So just to get specific, I'm going to be talking about a parameter we call eta, which is just the amount of HOC isoformal we make to this formal ion, HCO. This measurement at 300 Kelvin said this ratio is about 5. And then theory had said, well, it's anywhere between 2 and 100. And so there's quite a big range there that we were starting. So here's how we did the experiment. We shoot the water at the ion trap, of course, and we just let it react. You then take a mass spec after some wait time, and you see a mass spec like this. So there's beryllium, there's carbon, of course. There's H3O plus, because anytime you have water and ions, you always make H3O plus, we've learned. We understand how this is made and account for it in the reaction. You can make beryllium hydroxide because the beryllium itself can react with water, but we understand that reaction. And then the part we're really after is this mass 29 peak, this HCO or COH peak. Now you see we have a problem, right? We can use this to measure the total reaction rate, no problem. But if we want to know the branching ratio of these 2, we need some way of differentiating HCO plus from COH plus. They have the same mass, the mass spec can't tell the difference. So what we decided to do was to titrate the reaction products, so to speak. It's a little bit harder to break an CH bond than it is to break an OH bond. And so if you look at the proton affinity of different gases you could leak into the chamber, you find sort of ones in this range will react with COH, but they will not react with HCO. And so what we can do is add a gas in, it reacts with this one, makes a molecular ion at another mass, and so then we can figure out the fraction of these 2 isomers. The easiest thing for us to use is nitrogen, so this is just N2, so that's what we really wanted to use. The issue is that you all know nitrogen weighs 28, and if you add a hydrogen, it also weighs 29. And so we could titrate with nitrogen, but we would have, our new products would also be at the same point on the mass spectrum. So what we did was, turns out you can buy nitrogen 15 so that it weighs a little bit more. And so we bought this isotopically nitrogen 15 titrant gas, and we could introduce that into the chamber after the reaction and then react all the HOC away and put it at another point in the mass spectrum. And using that, we can measure this ratio. And what we found is we're able to measure the reaction rate. We're able to measure actually quite a few other reaction rates that are involved in the chemical network, but this is the main one, the tidal reaction. And we found that this branching ratio is about 2. So a little bit different than the 5 that the chemists or the astronomers were using. But this is where the situation kind of, the story got, I think, more interesting for me in that it illuminated something I hadn't really appreciated about chemistry. And that came about when Hua Gao, our theory collaborator, and Ying Li, his student and postdoc, started calculating the reaction. So they calculated the surface. They did quite a high level of theory for such a complicated surface, and then did trajectory calculations on that surface. And what they found is that their theory says that the branching ratio should be 50, not 2. What that means is what it means is that when this carbon ion reacts with the water, almost all of the products that are made are COH and not HCO. And even without looking at it too carefully, you can sort of see why. You don't have to do that many rearrangements. The sort of carbon is going to be attracted to the oxygen, and then one of these hydrogens needs to go away to give you COH. For the HCO, the hydrogen's got to find its way to the other end. Okay, so now we have a problem, right? Our experiment says that eta is 2, and the theory says eta is 50. Well, what we realized was that these trajectory calculations suggest that they say that about 90% of these products are actually above the barrier to isomerization, right? They have a bunch of internal energy. And those things are going to relax. And when they do, the density of states around the isomerization barrier is about 2 to 1 for HOC to HCO. And so if you include that relaxation in the theory, you predict that, well, eta actually should be about 2, not 49. And so this is actually kind of a summary slide of what we did. What this illuminated to me is that, when we talk about a branching ratio, it sort of depends on what you mean, right? It's a little bit arbitrary, of course, how trajectory calculations break up things. But, immediately after this reaction, about 98% of the atoms or the molecules are in this HOC state. So the branching ratio at that moment in time really is about 50. Now a physicist might argue with a chemist about what does it mean to call something HOC when it's above the barrier. I never won any of those arguments, so I'm just gonna still call it HOC. But then if you have time, and you certainly do in the interstellar medium, and maybe you do in your experiment, those states are going to relax. And when they do, they're going to relax in sort of, the ways determined by the density of states there. And so what happens is, if you look at this reaction from a statistical point of view and you say, what's phase-space theory say eta should be? It should be 2. And so when we measured 2, we're like, okay, this is a statistical reaction. But then the trajectory calculations say, well, it is, but only if you include the relaxation that happens after what chemists would normally call is the reaction. So that sort of illuminated something for me. And what do we mean by a branching ratio is sort of an ambiguous question, if that's the entire question. All right, so with that, now let me segue onto the quantum logic part of this talk. So I should say that the way I got into this is I've been working with Wes Campbell for a number of years. I think we started in maybe 2016 on some trapped atomic ion quantum computing. And Wes and I developed this 133 barium qubit. This is sometimes called the Goldilocks qubit. It had never been trapped or never been laser cooled before or used in quantum operations because it's radioactive and no one had, even the spectroscopy wasn't known. but we were able to trap it, measure the spectroscopy. And since then, we've been working on really high fidelity operations, right? We can do perfect single qubit gates. We can do state preparation and measurement with almost 4 nines of fidelity. And this is, led to all, like, I don't know if you follow the trapped ion quantum world, but IonQ has now switched to this ion. Some of the other companies are switching to barium as well. And it was sort of the fun of doing this, where we could have really high fidelity operations with our atomic ions, that got me thinking, and got Wes thinking too, about how can we port some of this to the molecular ion, so we can bring that control to the things that you and I care about, manipulating molecular ions at sort of, the ultimate level for whatever we want to do. Not the first idea, but probably the first good idea we had is this paper here, which came out since I saw you guys last. This is something we're calling dipole-phonon quantum logic. The idea is actually quite simple. If you have a molecular ion in a trap, right? Let's suppose it has 2 states. Those could be rotational states. They might be something more exotic, like a lambda doublet, omega doublet, and L doublet, but they're opposite parity states. So they have an electric dipole transition. And for our purposes, they're split by energy delta. And because they're an electric dipole, they have an electric dipole moment. The Hamiltonian not only has a delta over a sigma z term, it's going to have some sigma x term or some d dot e term that couples these 2 states. And it's important to remember that normally we apply an electric field to drive this transition, but any electric field can drive this transition. And these are ions in an ion trap, so they always see an electric field, right? In fact, they have a trapping potential that we approximate as a harmonic oscillator, 1/2 m omega squared x squared. So if you take the gradient of that potential, you actually have an electric field due to the trap, which is just, you take the derivative, so you have, an m omega squared x. And so this electric field really shows up here. And so the Hamiltonian you get, for those of you that think about these things, is just a classic sigma x from the dipole moment with an A dagger from the X. So what this does is it couples we call it the spin, but really it's, whatever this is, the rotational state or the lambda doublet, to the motion in the ion trap, right? So you can think about it as, if this atomic ion is wiggling, it's going to make an electric field, and this molecule is going to feel it. Now you probably say, Eric, this doesn't really matter. Rotational states are gigahertz, trap frequencies are megahertz. So this thing is so off resonant, it's never going to drive a transition. And that's true for a lot of molecules, but not for all. In fact, you can find a whole slew of molecules where there are opposite parity dipole connected states that are in the megahertz regime. And what's sort of exciting is probably the best class of those is realized by simply bonding an oxygen atom to the things you already laser cool. So calcium, strontium, any of the alkaline earths, you bond an oxygen to it to make an alkaline earth oxide ion. They have a very low energy lambda doublet that is perfect for this. So what does this allow you to do? Well, what doesn't it allow you to do, I guess? I'll give you just a couple examples, just in the interest of time, hopefully just to pique your curiosity, so we can talk more about it. You can do heralded state detection very easily. So these are the energy levels of the molecule plus the harmonic oscillator. So this is the molecule in the ground state with 0 phonon. So, you're perfectly ground state cooled. Molecule in the ground state with 1 phonon. Molecule in excited state with 0 phonons. On this axis is the trap frequency omega cubed. So this is effectively how tight your trap is. And let's just think of this as the axial direction in the trap. So we really just have some in-cap voltages that we can lower and raise. So these are just DC voltages. And what I'm doing here is changing that trap frequency over a range from below to above the frequency, the resonant frequency of the molecular transition. So when you do that, these states change character, right? On this side, it's exciting the molecule is a higher energy state with 0 phonons. Then on this side where the molecule being in the ground state with one phonon is a higher energy state because the phonon has more energy than the molecule over here. And so if I just ground state cool my atomic ion, and if my molecule is in the ground state, I do this, I'm in the ground state. If I happen to be in the excited state, the molecular excited state, I then ramp my in-cap voltages. I go through this avoided crossing. And if I do it adiabatically, I've now put my molecule in the ground state and I've made a phonon appear. Effectively, you change your in-cap voltages and it sucks the excitation out of the molecule and puts it into the phonon. You can then ground state cool, and that will give you heralded preparation of G0. So this is very, very similar to quantum logic spectroscopy, but instead of using a laser to drive some molecular transition here, we're just using the ion trap itself. Now, you can do a lot of things with this same Hamiltonian. You can do, for the experts, a single-sided Molnar gate. So you can entangle atoms and molecules. You can tangle molecules and molecules. It's really fast. You can do microwave to atom transduction, and this will work for a wide class of molecules. As we're writing this up and thinking about it, I realized that my old colleague, or my old collaborator, Kim Brown, who's at Duke now, had the perfect experiment for this. I knew that through a joint project we had, he had a calcium oxide project. And I called him on the phone. I was like, Ken, do you still have this experiment? He's like, yeah, it's collecting dust, but it's still there and it's under vacuum. And we decided to work together. I convinced him to do this. And so his group now, led by Lou and Evan, have done an amazing job of working towards this. They have now, this is a ground state cooling of a calcium oxide 2-ion crystal. You can see that they have really low phonon number. This is the blue sideband, the red sideband. They're sort of ground state cooling down to an average phonon number of like 0.2 these days. They have really low heating rates in this trap, which is important because if you have heating, it can fake your preparation. For the out of phase mode, so this mode is the one we're going to use. They have sort of a phonon every 2 seconds. So this is really nice. And they have now, over the last few weeks, been able to demonstrate this ramping, that you can ramp from below to above this molecular resonance without heating. Because, if you just grab your ion trap and go like this, you're going to excite the oscillator. And so this is, the blue and red sideband before and after ramping. And there's really, within air, there's no heating. And so, what's up next is they're now beginning to work on this heralded state prep. So stay tuned for these guys. I'm really excited to see what they'll do. Okay, so now let me turn to my last topic, which is probably the thing I'm maybe even more excited about. And that is this is again with Wes Campbell, my longtime partner in crime. And this is this thing we call EGGs, or electric field gradient gates. And this is, I think, broadly applicable for molecular ions. The point of EGGs is really in the title of this paper, and that is it allows us to do laserless quantum gates, which I think is really important for molecules. I didn't say that earlier. If you're involving photons on your molecule, there's all sorts of bad scattering that can happen. So if you can do things without lasers, I think that's a plus. And it doesn't require ground state cooling. You can do it with ions and thermal motion, which is also a big deal, I think. All right, so how does EGGs work? Let me explain it to you sort of the basic idea of some of the physics classically, and then I'll flash up some Hamiltonians and show you what you can do with it. Let's imagine we have a molecular ion and some molecular ions in a trap and maybe some atomic ions. The molecular ion has some ground to excited state transition. That's at energy delta, just like before. And because it's an ion trap, there are now motional modes of the crystal. And so I'm just plotting one of the modes. And let's just take this as the radial center of mass mode for those of you that know what that is. I can apply voltages to my ion trap to trap the ions, of course, but I can also apply oscillating voltages to the trap that are resonant or nearly resonant with this molecular ion transition, right? So this could be rotational, these could be 10, 50 gigahertz. They could be lambda doublets. They could be, lower in frequency. But this delta no longer has to be near the trap frequency. In fact, you don't want it to be. You want it to be quite a bit big. So this would work for, a lot of molecular ions. And I can apply that voltage in a dipole configuration where, my microwave, I put the, positive polarity minus negative polarity here. This makes mostly a uniform electric field at the ion, and I could drive transitions between G and E, of course. But I don't have to do that. I can also apply it in a quadrupole configuration, just like I would apply my trapping voltage. But again, these are, at microwave frequencies, and they're nearly resonant with the molecular transition. Let me show you what happens if I do that by applying two of these tones. So I'm going to apply one microwave that's resonant with exciting the molecule and destroying a phonon, so-called red sideband, and one with exciting the molecule and adding a phonon, a so-called blue sideband, right? But I'm applying this in this gradient configuration. And let's just think about it classically for a moment. These are dipoles or electric dipoles. So the force they feel is given by the gradient of d dot e, right? The potential is d dot e, so the force is given by the gradient of that. Dipoles, electric dipoles, feel forces not from electric fields, but from gradient of electric fields. So now we have a gradient. And we know what the electric field of this ion trap is. It's just a quadrupole. You take that gradient and you get something that's constant. There's no x dependence. And because we have two tones, we have one that's oscillating at the red sideband and one that's oscillating at the blue sideband. But, you remember your math, and cosine of delta minus omega plus cosine of delta plus omega can be written as cosine of delta times cosine of omega. So this looks like a transition, or looks like it's the same as an oscillation at what we would call the carrier transition at delta, with what we'd say is full amplitude modulation at cosine omega q. So it's now it looks like something oscillating at the molecular transition frequency times something oscillating at the ion trap frequency. All right. Now think about what it means, what the dipole moment of one of these molecules actually does in the lab. And let's look at two states. We'll look at what we would call the plus and minus states, or the plus and minus x states. So these are going to be G plus E or G minus E. Right? If I make a superposition of these states, they have a dipole moment in the lab frame, but they're oscillating back and forth at delta, at cosine delta t, right? So I make a superposition of G plus E, and I get a dipole moment that just does this in the lab frame. But notice, I now have a electric field gradient, or a force, that is also oscillating at delta. So while the dipole moment averages to 0 in the lab frame, the net force is sort of rectified by the fact that I'm moving the gradient in phase with the dipole moment. And so the average force is non-zero. And in fact, the sign of it depends on the quantum state I'm in. If I'm in plus x, I get a force one way. If I'm in minus x, I get a force the other way. You can work this out quantum mechanically, and what you find is this time evolution operator where plus x gets a displacement. This is a displacement operator for the harmonic states in one direction, and then the minus x get the other. All right, I see you. I will wrap up in like 2 minutes. Is that cool?
Yeah, that's cool. All right.
Yeah, thanks. I can't see my clock. I'm sorry. All right. All right. So I wasn't going to show this slide anyway. Just to point out that, you can work out what these Hamiltonians are actually correctly using quantum mechanics. And the main point I want to make is that this Hamiltonian is the Hamiltonian that ion trappers dream of when they're trying to build a quantum computer. They only get it when they get in what's called the Lambdicki regime and they've ground state cooled. We get it for free because our ion traps are shaping the electric field to be exactly the Hamiltonian we want. And so with this, you can do state preparation and measurement. You don't need to really worry about the details. The point is, for very modest parameters, 15 volts of microwave on my ion trap, I can do state detection in a few microseconds, and it's done in a quantum non-demolition way, so I'm not affecting the molecular state afterwards. And I can also do entanglement very, very fast and very insensitive to the ion motion. You know, here's sort of, these are just sort of normal looking graphs for when people are talking about 2-qubit gates. You see that we can do gate times on the order of microseconds with really achievable voltages on our trap. All right, we built a system for this. It needs to be cryogenic. This is what we've been working on. Mostly, I'll just put this up for those of you that might want to talk about it later. We have a kind of a neat trap design that is self-aligning. You can see here's the system. We can cool it down to about 4 Kelvin now in a number of hours. This is a measurement of how much vibration we get. This is closed cycle, so you normally get a lot of vibration, microns or more. We're able to get less than 25 nanometers, which is plenty for what we need. A few months ago, we trapped calcium in it. Calcium is like the one alkaline earth we hadn't trapped pretty much at this point, but it turned out we needed it for this experiment, so we had to spin all that up. We have great trap operation. And what's really fun, if you're an experimentalist and you're thinking about going cryogenic, it's really hard, but once you do it, it's nice because our trap lifetimes are effectively forever. We can trap for days. You can turn off the laser cooling and turn it back on and still have a crystal. It makes things really nice. All right. We have in another system now begun to trap the molecular ion we want to work with for these electric field gradient gates. And so hopefully over the next few months, we'll start to see some of these operations. All right, so let me summarize and stop so Roland doesn't get too mad at me. I told you about this chemistry experiment where I learned what a branching ratio means a little bit more, or maybe I really learned what it doesn't mean. I told you about dipole-phonon quantum logic, this quantum logic with a battery, and this electric field gradient gates. And I'd be happy to talk more. And I'm sorry for going over time. Thank you, guys.
Thank you, Eric. I hope you heard the applause, and there will be questions now. Thank you very much. Huh? Let's start.
Yeah, I hope you can hear me, Eric.
I can, yes.
Yeah, okay. Yeah. So I really like this idea of the quantum logic with the molecular ions. And I'm one of those ion trappers who dreams about the Hamiltonian you were showing. And actually, yeah, okay, so you were saying people need ground state cooling. Well, this is not quite correct. The Milne-Sørensen gate doesn't actually...
Yeah, you need Landicki regime,
right,
but honestly, that's basically ground state cooling is what I would have said if I wasn't running overtime.
Yeah, okay. Of course, there are a bunch of other varieties of this gate that also don't require basically ground state cooling or the Landicki regime. But actually, what I was wondering, you rely a lot in this scheme on nulling the microwave, right, at the position of the ion. So this reminds, because basically you're making a quadrupole field, it reminds me a bit of like quadrature micromotion, where it can turn out to be really
it's
hard
exactly right
to do this.
All right.
So
yeah, I wish I was there because I'd love to go. Go ahead. Sorry.
Yeah. So did you kind of estimate this on how sensitive you would be, on this effect?
Yeah, we spent a lot of time on exactly this. So what happens is if you don't null the microwave at the position of the ions, you get this term here. So X equilibrium. Let me see if this is the right slide. Let me go back. One of these slides has what I want. So X equilibrium is exactly, how far are you away from the null? When you go away from the null, you no longer null the microwave. And so now you have carrier transitions. And what's exciting about this is if you are on the null, you don't have carrier transitions, which is nice. Something that, would be nice. And so you can handle carrier transitions with a few tricks, right? You can do pulse shaping like you do for atomic ions. And it just depends on how slow you're willing to go effectively to how well you can handle this. What I can say though, which is the real answer to your question to show that your quantum student is a very good one, is the molecule that we want to work with has a delta of 40 gigahertz. But we were very scared about exactly what you said. And so instead chose to start with a molecule whose delta is 100 megahertz. And at that level, I'm not too worried about it.
Yes,
so we're going to
I
start
agree.
low.
Yeah, that's smart. Yeah.
Yeah.
Further.
Thanks.
Further.
Those are a lot of. Yeah, I wish we were there to talk because I think we could have a fun discussion.
Is there another question? I don't see at the moment. Okay, then I think I'll end the discussion here. Thanks very much again, Eric.
Thank you guys so much. I really appreciate it. All right.